Welcome everybody to the Journal Club. I'm Rosa Gini, the Vice President of VAC4EU and former responsible of the organizing committee of the Journal Club. So this is a great joy to announce that the Journal Club had started, I think, in 2022. And then we've been on a kind of pause for 1 year, and a new group of young and strong people has taken over. So the spirit of the Journal Club remains the same. So we meet to have fun with science, to discuss about papers that we don't understand and try just to make questions, maybe stupid questions, but to discuss together and try to help each other understand. So it's a great pleasure to introduce the new Journal Club Organizing Committee, Martin, Giorgio, and Sima herself. Please, Martin.
Hi, Rosa. Thank you very much for your words. And hi, everyone. We are super happy to have you here. Thank you very much for joining the meeting. And yeah, like Rosa said, this is the first session of the new season, because this is a new season of the Journal Club. And we are super happy in launching this today with the spectacular topic that will be given by Sima. Welcome, everyone. My name is Martin Solórzano. I work in IDIAP Jordi Gold in Barcelona, and beside Giorgio Limonchella and Sima Mohammadi, we're gonna lead the new season of the Journal Club. So I will give the word to Sima just after reminds you the objectives of the Journal Club. This is a monthly informal gathering designed for researchers at all levels. So everyone is welcome in this meeting, and we discuss many topics, especially papers in public health, epidemiology, biostatistics, and data and medical science. But we are open to many types of papers, so we are not just close to these topics or these areas. So everyone who would like to present a topic or a paper are welcome to send their suggestion, and we're gonna evaluate all these proposals. What else? We discuss scientific papers across a wide range of topics related to these areas I mentioned already. And this is a space to ask bold questions. You know, there is no stupid questions here. You can ask all your questions. You can solve as well your doubts and your questions. We're gonna try to challenge your assumptions and sharpen your thinking as well. And this is the purpose of this meeting, you know, to express what you think and how to solve all these matters. Yeah, now it's the time for Sima and Giorgio to introduce themselves. And thank you very much again.
Yes, maybe I start and then I leave the floor to Sima so we can go on with the presentation. So hello everyone, thank you for joining. I'm very glad a lot of people joined the first meeting of the new season of the Journal Club. My name is Giorgio Limonchella. I am research fellow at the University of Florence, actually for just a few more days. I'll be starting a new position in the University of Bordeaux very soon. And I'm a statistician by training, and I've been involved in VAC4EU with the Ask Tuscany with Rosa, and I'm very glad to be part of the organizing committee of the VAC4EU. So thank you for joining, and please, Sima.
Hello, everyone. Welcome. I'm really feeling a fresh start with this new launch of the Journal Club. I'm Sima Mohammadi, and I am a medical doctor by training. And it's almost 3 years I'm doing my PhD. I'm in the last year of my PhD, and I'm doing my PhD on pharmacoepidemiology. And within VAC4EU, I have been working on code list coordination and semantic harmonization, which is the main reason that it brought me here to be interested in AI and how it works. So I'm excited to present it. If I don't know if Ashton, you would like anything else to say, otherwise I can start.
No, I think you can go ahead.
Okay, perfect. So welcome to this Journal Club. It's great to see some new faces here, and to get the sense of a room, I plotted this figure to show the distribution of participants. It's great to see such a mix of background here. That's perfect for this topic because it really benefits from all your perspective. I mean, data analysts are here, medical experts, statisticians, policymakers, epidemiologists, data managers, and all of you. Some of you, you didn't have explicit job title, so I categorize it as others, but it's perfect. So I think since everyone explained about this journal club, I skip it and I'll jump straight into the topic. Today, I will present this perspective review titled, Will Generative AI Make Common Data Models Obsolete in Future of Distributed Data Networks? This article is authored by Jeffery Painter, who is also with us today. I don't know if he has joined yet or not, but if he's here, Jeffery, thank you for joining, and you will make this discussion even more interactive. So feel free to clarify any point at the end of the presentation. Just a head up before we start, I've got, because we have people from different backgrounds here during the presentation, I will briefly explain a few technical terms as we go. So I added also a few figures from the referenced article that was in this paper. So I added some figures there for better visualization of the concept of this paper. Here's the roadmap of our session today. I begin with the background information on common data models, the history behind that, and the key challenges we have with common data models. Also, I will go to the objective of this paper, and then I will cover the discussion and conclusion, which is focusing on the proposed building blocks for the next generation of the safety surveillance studies. And please note that this manuscript is a perspective review, so it is synthesizing insights from literatures and experts' consensus, and it doesn't have the results section. And finally, we will spend about 20 minutes for discussing the strengths and limitations of the paper and addressing your questions. As you know, real-world healthcare data are really essential for research and pharmacovigilance and patient monitoring. But the challenge here is that these data are highly heterogeneous and they differ in formats, coding system, database structure, and even the language. In addition, the numbers of databases are growing these days. So without this common framework, integrating information from multiple sites is nearly impossible. This is where Common Data Model, or CDM, plays a crucial role. CDM actually provides a standardized schema so that each participating site or database can transform their local data into this shared structure. So as a result, researchers can execute the same analytic queries across all sites without moving patient-level data to the central repository. And this is the core principle of today's distributed data networks to preserve patient privacy. CDM have been truly a game changer. They have enhanced the interoperability, they have improved their reproducibility, and they enable the federated analyses across different sources, but they also have some downsides, such as they are costly and very resource intensive, especially for the ETL process. I mean, for the extract, transform, and loading the data, it requires a substantial manual effort, not only to produce and maintain it, but also to continuously update the CDM because databases are updating. Also, there is a risk of information loss even during the ETL process. Also, we might have the semantic distortion because unclear assumption during the ETL can introduce bias or misclassification. And people who are ETLing, they can have a misunderstanding of the process or changing the semantic basis behind that. Another limitation in the ETL pipeline is that they are usually very slow. I mean, they may delay the rapid cycle analytics in the situations such as public health emergencies. Moreover, inconsistencies across these different common data model or even across implementing the same common data model, it can yield different results for the same research question. So yeah, these are all the limitations we have. And now it gets even harder because on top of the CDM challenges, we also face some terminology and semantic issues. For example, mapping between different coding systems such as ICD, SNOMED, READ codes, and many others. This is challenging because this variability in medical dictionary across different healthcare informatics system and a different level of granularity of this coding system is not always a straightforward process to map them. And in addition, these medical dictionaries, they are updating in versions, and frequently they are introducing new codes or expiring the previous codes. So, and sometimes the definition of a key variable can differ from site to site. So together, all these semantic challenges and harmonization, it makes it more difficult. Here is where AI techniques can help and actually help and support automating the mapping process between terminology. And as a result, AI can reduce the manual effort while also enhancing the accuracy. One of the biggest challenge in the real world research is finding a database that actually fits your study purpose. Each database might cover only certain population, which can create selection bias. Also, differences in healthcare settings, such as primary care, secondary care, emergency room, and many other existing settings, it can affect both the data access and the level of details in the data. So also, there's a need for up-to-date information in the database. So this means these are all the challenges that make it hard to decide on selecting a fit-for-purpose data source. SPFD, which stands for the Structured Process to Identify Fit-for-Purpose Data, is a framework that helps address these issues. This framework is conducting a kind of feasibility assessment, which is a step-by-step guide to evaluate each data source for the relevance of data, completeness, quality of the data, and some other criteria to ensure that the data are fit for purpose. Specifically, this is important for regulatory decision-making to choose the fit for purpose data source. And here I put a link of the paper that this paper is on specifically on the SPFD framework, and this figure is from that paper. And of course, we cannot overlook the privacy and the ethical concerns. Strict regulations such as GDPR or General Data Protection Regulation, they control on how personal health information can be collected, stored, and shared. This is really good to protect patients' confidentiality, but it makes data sharing a bit slower and more expensive. So given that each country has their own governance rule, as well as some technical barriers in between, this regulation complicates the data exchange and might delay in decision-making. The COVID pandemic is a perfect example here. During the pandemic, CDM-based networks proved a really valuable role, but the data processing requirements were sometimes too slow to meet the real-time needs. So all these challenges made regulators think about a more efficient approach for the safety studies. Now, let's take a brief look at this history of data integration and quantitative analysis in healthcare data. This paper is organizing the history of data integration into 4 generations. The first generation, introduced in 1917, 1970, when each database operates entirely on their own with no common standard. So results were siloed and cross-study comparison were hard or even impossible. Then the second generation in 1990 was when medical dictionaries such as SNOMED and ICD introduced, which made the multi-database meta-analysis possible. However, it required some intensive manual effort, even though they had a shared protocol, but still analysts had to maintain a separate programming code for each database. The example of a project that has used this second generation are Canadian Network for Observational Drug Effect Studies and PROTECT project, which is a European consortium for pharmacoepidemiological research. Then the third generation emerged on about a decade later, on 1999, with the introduction of common data models. It was quite a significant evolution. CDM allows each site to return the patient data level locally while executing these standardized queries on a harmonized schema. They've used shared protocol without requiring access to individual data, and this greatly improved the interoperability and reproducibility. There are many projects nowadays using the CDM, like IMI Conception, Vaccine Safety Data Link, FDA Sentinel, ODC, DarmendRA, and many others. And some of them has their own CDM structure. Not all of them are using the same structure. And as we mentioned earlier, this CDM might risk the information loss during the ETL mapping. So here is where an alternative approach, such as generalized data model or GDM, were developed. This GDM developed to balance the standardization and reduce the information loss. What is GDM? GDM is a flexible schema that preserves the source medical vocabulary and data provenance in the raw format without changing the format, and capture the hierarchical relationship of the clinical codes to ensure that the full depth of the original data is retained. So it's a great idea for reducing the risk of information loss. But GDM is kind of a complementary to CDM. GDM doesn't force the data into a rigid domain such as visits table in the CDM. It is just good for, not just, but it's good for reducing the risk of information loss. Each database can load their data into GDM as a kind of staging layer and later transform it to a common data model for multi-database risk. Yeah, please.
Sima, sorry to interrupt. I think that you are, at least in my screen, your slides are not proceeding. It's still stuck to the history of quantitative analysis in healthcare data.
Oh, no, sorry. This GDM was part of this third generation. That's why I'm explaining this in this slide. Yes.
Thank you. Thank you.
Sure. And this design of the GDM, so it reduced the information loss, and this GDM has its own complexity, like the complexity of working with heterogeneous data in a native format. It may require more sophisticated analytics tools, more expertise needed, and require longer timeline for analysts. So now let's take a look at two types of data here. It's important to know the differences between these two types, centralized and decentralized data. What are they and what advantages and disadvantages they have? In the centralized model, all patient-level records are pooled into a single repository, which simplifies querying and helps standardization, but it raises some significant privacy and security concerns. But in the decentralized model, the data remain at the local site and only analytics queries are distributed, and then the aggregated results are then returned. Although this decentralized model preserves the privacy, but it requires a greater coordination among sites. It also has some limitation, like this decentralized model. It may increase the risk of data loss even if the provider withdraw from the network. So you don't have access to that information anymore. In addition, because each site retain the control of their own data or record, there can be a wide variation in data collection method and quality of the ETL process. So decentralization can also limit the speed and depth of the analysis. And at the end, so it may introduce a low quality or poorly curated data from the participating sites. So there should be some rules to control those, no? Now, the key objective of this paper is asking actually, can generative AI and knowledge graph together eventually reduce or even eliminate the reliance on the common data model? And specifically, it will set out to explain why the transition from CDM to the AI-enabled method might be necessary. And it will propose the fourth generation of distributed data network analysis by applying the AI-based standardization of raw data. And it will discuss the potential of generative AI and operationalize the, it will give you an insight of what are the challenges if we want to use this generative AI. So now let's get to the discussion. Why we need this transition from CDM to AI? As I explained in the background, there are several reasons to consider to move beyond this traditional CDM. To summarize those limitations, first, healthcare data are expanding rapidly, and also both in volume and complexity. Second, there's a growing demand for the rapid safety studies, which conventional CDM might struggle to support that. And third, common data models are costly, labor-intensive, time-consuming, and can reduce semantic loss. And it can increase the semantic loss risk. And on top of this, overcoming semantic harmonization, regulatory and ethical challenges add other complexities to this limitation, which all of these may result in prolonging the insight generation. That's why we need to look for a better, faster, and more accurate way to generate insight. Now, let me walk you through the 5 building blocks that this review proposed them as a necessary blocks for creating the 4th generation of distributed data. The first block is data common. Second is AI-enabled data access. The third one is knowledge graphs. And fourth is automatic code generation. And the last block is governance and trust. Now, what are these? The first block is common data. A data common. A data common is a shared environment with common APIs and tools where the data itself stay at the original site, but the metadata described in those data are openly visible. This design supports the centralized analysis and protect the privacy. So basically, in a simpler word, these common data are like database catalogs describing the database features, data in depth. The second block is the AI-enabled data access. What does it mean? It means AI can automatically locate the right data source using the metadata information in a common data that you provide, and then retrieve the necessary information and only immerse the aggregated summary of that to you. Then here, a large language model can integrate and interpret this diverse data set in their native language without a need for a traditional CDM conversion. So instead of doing a heavy ETL step to fit everything into a CDM, you can just easily query the raw data directly and even let the data be structured and evolved dynamically. This means less manual effort, less burden on the data providers, and much faster turnarounds. And of course, privacy stays intact here because nothing leaves the local servers. Then the third block is the knowledge graph. A knowledge graph is a structured network of entities and relationships. So specifically, it is a multidimensional map that links diseases, drugs, genes, procedures, and all types of data in medical data. Sorry, maybe I have a better. I think I think I have a better overview here. In this picture of here, you can see a good overview of knowledge graph. This is how knowledge graph looks like. It links all the relationships between the medical data. So, now talking about the knowledge graph. Then after knowledge graph could link all these data together, then AI can support exploring this map and define phenotypes and even spot the hidden pattern using the relationships defined in knowledge graph. So basically you can predict drug safety signals, which is very important to speed up adverse events detection and also very important for personalized medicine when you can predict the hidden pattern. Examples of the project that nowadays are using this knowledge graph and AI together to predict the hidden patterns are first Phenolator, which is a project that uses this AI and knowledge graph to link the genomics, proteomics, clinical and chemical data. And the other project is Planet, which is a project which combines clinical and biological knowledge graphs to predict the drug safety outcomes earlier in development. And of course, this AI-driven system requires a rigorous validation and benchmarking against the trusted safety data sets. Another key role of generative AI and knowledge graph together is that they are harmonizing medical terminology and keeping pace with evolving medical knowledge. I mean, when medical dictionaries are updated or new diseases are introduced, the AI can quickly adapt those changes. Example of a project that uses knowledge graph and AI to do the semantic harmonization for the medical terms is FIRE GPT. It's a nice example because this project is using these two techniques to convert the free text EHR notes into a structured FIRE standard. And for those who are not familiar with the FIRE standards are the web-based standards for exchanging healthcare data electronically. Although using this knowledge graph and AI in pharmacovigilance is still limited to few studies and few examples, but it's promising for improving rapid safety surveillance and supporting the evidence, supporting the prediction, preventative and personalized medicine, as I said, specifically through their predictive potential. And then the fourth block is automatic code generation. So traditionally, researchers must disseminate code SQL or R script to each data partner. But nowadays, generative AI, specifically large language models, just a question like, what is the incidence rate of event after exposure can be translated into an executable code by using this AI. So you don't need to write the code yourself. But we all know that these large language models can hallucinate, no? Then here is where RAG comes in. What is RAG? As you see, RAG is retrieval augmented generation, and basically is an architecture that can ground the LLM on the validated sources such as clinical guidelines or peer-reviewed paper. so that it improves the accuracy and reproducibility of the AI. Because AI, if it is not granted on if it is granted on a web and not granted on only validated sources, it may hallucinate. So here is where RAG helps a lot in granting those on validated sources. And finally, the last block is governance and trust. We need to ensure that AI systems are reliable, safe, and trustworthy. This means we need a clear legal agreement and protection between the data holders and researchers. So this article suggests some methods for keeping this governance and data security. Methods like data authentication through digital signature, which is it's really good for privacy preserving and keeping the quality of the data. By authenticating through digital signature, you can verify the database's how do you say, actors. And some methods for privacy preserving are mentioned in this paper as federated learning, which is a method that the machine learning approach lets many different sites to be trained on a shared model, but locally. So they don't ask for the data, for the raw data. They can take the model in each site and train the model based on their existing data without disseminating any raw data. Another way to keep this privacy preserving is sandboxing, which is a method actually for that you keep data inside the protected environment, and analysts can run their code or experiment without copying or removing the original data. Or another suggested method is non-PHI summary, which is a method where all personal identifiers are removed or aggregated results only are shared, so without exposing individual patient. And of course, rigorous quality check steps here is important. For example, ODC has an environment, has lots of quality check steps that you can use it as a main input to help AI learn on the quality check steps. To summarize, this architectural framework of these 5 building blocks is explaining that to enable the 4th generation framework, we need a decentralized data common with key capabilities such as first, data authentication. Second, having a rich metadata describing coding schema, version, and source language of each database. And third, common data should be aligned with knowledge graph. And then the whole framework allowed the data to remain in the native language, reducing the semantic loss and information loss. And when it is paired with AI, it can use the information in the common data, retrieve the necessary information while preserving the patient's privacy. Now, let's see what's new if we adapt this AI approach. So instead of transforming every data set into a common model with its time-consuming ETL process, AI can interpret the heterogeneous data dynamically and harmonize them on the fly. And it will reduce the need for extensive data preparation. Generative AI and knowledge graph together can automate terminology mapping and enhance the ontology consistency, and subsequently lowering cost by also preserving the original semantic of the data, which reduce the information loss. Also, considering that medical terminologies are evolving rapidly alongside with biomedical research and updates in medical knowledge, AI can adapt this update faster than human. There are studies that have demonstrated that this large language model can learn from the structure of the specific database and then generate the code specifically for that database. The same code then can be adapted to other sites based on their structure. So it can be reused, but based on their structure, which saves a lot of time and resources now. So in addition to all of these, generative AI also supports many other activities in research. It can help define phenotypes, summarize information from unstructured data in EHR, in electronic health records. It helps in phenotype validation, and also it can guide the study design specifically for causal inference by finding the hidden patterns. And in theory, AI could make analyses faster, more cost-efficient, and more accurate. And at the end of the day, all of these can support better patient outcome and more informed public health decisions. Now, what are the big challenges with the new techniques? Still, there are trustworthiness, privacy, and governance concerns that need to be solved. Key challenges here are that this AI might affect the trustworthiness by lacking the transparency or wrong model assumption, data privacy and security concerns, and model performance. All of them are a concern still in the AI field. So we need a good quality check and clear validation step to prove that the results are accurate. Existing frameworks like ODC have some quality check steps that they have a quality check step on the common data model. So this can provide as a foundation for developing an AI-specific quality check standard. And then, the paper at the end concluded that knowledge graph and AI in pharmacovigilance are still at the earliest stage, but early results in few studies has been promising. While common data models remain valuable and will not disappear overnight, the field is clearly moving toward a more dynamic AI-enabled approach. And electronic health database, data networks are expanding, so this technology can harmonize this heterogeneous data and enhance the semantic harmonization and reduce the operational barrier in federated networks. Generative AI and knowledge graphs together could make CDM less central, but the most realistic future is a hybrid model where CDM provides stability and standardization, while AI and large language model and knowledge graph can add up to the speed and adaptability of the CDM. Actually, this review article emphasized that no single model offers a perfect solution. And this is true. There's no perfect solution here, but at the last point, our goal of using all these techniques is to deliver a faster, more reliable, and to maximize patient safety and public health impact. And to use this new technology, we need collaboration between data science, clinicians, regulators, policymakers, and that's good that we have all of them today here. Here, I'd like to highlight the sentence from the article that really caught my attention because it really impressed me. It's a nice sentence. It says, a key question is not just how many data sources have been converted into common data model, but how many remained unavailable and why? This is good. Just think about it, yeah. And now I'd like to open the floor for discussion on the strength and limitation of the paper. And then I already noted some of the strengths that the paper really give a good overview of a history of common data model. It highlights the limitation we have in data integration and CDM limitation. And it proposed a clear framework for the next generation of a federated data analysis. But do you think, from my perspective, Do you think that the paper provides enough practical evidence to support such a paradigm shift, or is it just more speculative? We can discuss it later. That just as a last point to help you get to start the discussion, I also prepared a few questions here, so they may overlap with your question. So please feel free to share your perspective and raise additional points. I think my question here are, what infrastructure do you think is needed to deploy this generative AI and knowledge graph? And second, what would be the biggest barrier to achieving this fourth generation? Is it technical, legal, organizational? What is it? Thank you so much for listening.
Thank you,
very much.
Sima. Yeah.